Hello everyone, welcome back to the second lecture of week 8. So we'll continue our discussion on instruction fine tuning. So we will talk about a few things like instruction fine models are quick learners. So in the last lecture we talked about the cross task generalization, that you train them on one task and they are able to perform well on other tasks also on which they are not trained. So but we will see that they are also quick learners. If we give them some data about the current task, they'll do better. So we'll talk about Flan models that have been one of the very popular models in the instruction fine tuning paradigm, and then we will end this with telling how do you self-generate instructions. Like it's very cumbersome task to have humans generate this always. So can we have models also generate instructions? So that's what we will end with. Okay. So just a quick recap of what we had done. So just to contrast with other learning paradigms, so you have this pre-training fine tuning paradigm. So where you take a pre-trained model and you fine tune on the data for the task, right, from the fine tuning domain, and you continue training all the parameters, right, or you can fix what parameters you will freeze and others you will train, and this can be an expert prediction objective if your task is that, or something else, right. You can have MLM fine tuning, masked language model type of fine tuning, where you have supervised data and task specific loss. So this is typically used in the encoder kind of scenario, and this was more like a decoder kind of scenario, right. So when you do fine tuning, you can have fine tuning in encoder, that is MLM kind of model, or decoder. So encoder, the fine tuning happens as we understood by task specific loss, right. In BERT you had many variations, and in decoder like GPT there was no variation. You simply give the describe the task, and next word prediction is how you perform the task, right. Except in GPT, right, where we had this extract token, but later on that was not used. So this is typically two kind of fine tunings we talked about. You can do parameter efficient fine tuning. So this is something we will discuss in this course, right, in some later lectures. What is instruction fine tuning though? So you will start from the pre-trained model. You will give the supervised instructions, right. So you will give the, remember, instruction plus input, and you will let the model predict the output, right. And you can again do the fine tuning with the same next word prediction objective, right. The objective across these two does not change. The same objective. What changes is the data. So here you are giving just the input, and here you are giving instruction plus input, right. So that's the simple change that is happening from normal fine tuning to instruction fine tuning. You are so the model has now learned. Now learning that given this instruction, how do I do this task? Right. This is the reasoning that the model is learning now. So this is an example of an extended instruction where you have a definition of the task, like creating an answer to complex question from a given passage, and you have to understand multiple sentences and same type as the answer type, and you have given the instruction. You have some emphasis, like if you find multiple spans, please add them all as a comma separated list. So you are giving even the format here in the emphasis, and please restrict each span to 5 words. So you are describing it, right. You may want, otherwise you will code it, right. You will say, okay, I will code it such that the output span are restricted to 5 words, but you are describing now in natural language. And then you say, okay, what do you really have to do in the prompt? So write an answer to the given question such that the answer matches the answer type in the input, and give it the passage, the question, and then you have to give the answer, right. So you will have multiple such instances by which you will do instruction fine tuning, and then you can do inference based on instruction fine tuned model. How do you create these in scale? So typically what you do, you take data set that are already available and create some key value pairs, right. So like say from sentiment analysis data set, so you can define labels are 0 or 1. So 0 means negative, 1 means positive. So you can define keys and values. So data set, I'm getting text and labels, right? That's all, I'm getting text and labels. So now text becomes a placeholder, right? Label becomes another placeholder, and I can write my template using this keys, and whenever I have this template, I can fill it with the values, right? That's the idea of doing it at a scale. So you, for each different data set, different task, you can create each key and value, and then you may have multiple templates, right? So that is another very important point about instruction fine tuning. So you may want to fine tune by multiple different paraphrases of the prompt, right? I mean, you will want to describe the task in multiple ways, and still the model should be able to understand it and perform the task. Like for natural language inference, you can have premise, hypothesis, and the label. It has the 3 different keys, right? And these are some examples. Extractive question answer, you have context, question, and the answers, right? That are your 3 keys. Now, once you have defined for a data set what are my keys and you have the corresponding values, so you can have multiple kind of templates, right? And why? Because it's useful that the prompts are diverse, so that you are not fixating again that for this kind of problem I will only focus on one prompt. No, let it be generalized, because the task can be described in many different manners, right? I mean, many different ways. So you can create paraphrase of this template, like this is a template. So you will put text, right? You'll put the text here. How does the reviewer feel about the movie? So text is nothing but the movie review, right? That's coming from the value for this key. And then another template is the following movie review expresses what sentiment, right? Another way of saying the same thing, and you put the text. Or you can put the text, did the reviewer enjoy the movie, right? So you have different templates for sentiment analysis. Same for extractive question answering. Given so you have the context from the passage, from this passage, the context, and you put the question, answer the question given the context, right? I mean, this is one thing. Or answer the question given the context, you give the context in the question and let it answer the question. Or given the following passage, answer the question. You have the question and let it generate the answer. So on. Similarly, for NLI, you can have multiple templates, right? So what you can do, human may, in the annotation guideline, you may have one particular template. Humans may create one template, but you can use language models to paraphrase that, and you create multiple templates, and that can be used for tuning the models. Okay. So what is something that they understood in instruction fine tuning? So we said they are good at cross task generalization. You train them for one task, and they can do a new task. You can train them on multiple tasks in instruction fine tune, and given a new task and the instruction, they can do the task very well. But somebody may say, okay, what if I want to do my current task even better, right? Because we are finding something called supervised upper bound. So I already have data for my task, right? So suppose I have a task A, I have sufficient data, right? And I can use T5 model and train on the entire data. I get some good Rouge score. This looks like summarization, you are using Rouge score, Rouge L, right? Now, can I use instruction fine tuning to even improve on top of supervised upper bound? I mean, this is what we learned is good if we do not have sufficient data to train my model, right? But if I already have sufficient data, can I do better than what I am getting by a normal supervised fine tuning? So they saw in this paper that yes, they are actually quick learners. So like conventionally, if you do few shot inference, the TK instruct model, so this gives like 54.3. That's okay. But what if I further instruction fine tune it on this particular task itself, right? I mean, because you can have the instruction for this task, you have examples from the training data. I can pick some examples from the training data and further fine tune it. So you take TK instruct and further fine tune using 6% trained samples, and you get very close, right? Just with 6% of the data, you get close to what you were getting with 100% of trained data. Okay, what if I take more data, 25% data, you are able to surpass the supervised upper bound, right? And that was very, very exciting. I mean, so that means yes, so you can use it for tasks, you can use it for training the normal way, instruction training the normal way, and it may surpass the supervised upper bound. Okay, so this was something that came out. So So, this is like the SOTA model, the previous best model, uh, with an, I mean with 1000 samples, and if you uh, keep on having more sample, I mean keep on taking all the data, you already get 73.14 with the instruction fine-tuned models. And if you keep on giving them more examples, this was for the task, it was doing better. Remember, we saw um, in the scaling laws that if you give a lot of instances per task, it does not help the cross task generalization, right? But for the same task, if you want to improve, more examples are helping, right? So, it may not help the cross task generalization, but for this task, you are able to improve the performance continuously as you give more and more training samples. So, this again is a very nice way of improving performance on tasks, where you can define instruction. So, you can have summarization task and for a particular domain, and you have some data set. So, I can start from an instruction fine-tuned model and further instruction fine-tune it on that particular data set, right. So, I can do fine-tuning through instructions, and that I hope to get better performance than just doing a fine-tuning on a normal model, right, complete supervised fine-tuning. So, yeah, given that background, so Flan models are again very popular. From Google. So what so they followed very similar kind of pipeline like supernatural instructions. So they will pre-train and then fine-tune on a bunch of tasks, and then they will generalize to unseen tasks, right. So so they had taken 1800 tasks, okay, and they did instruction fine-tuning. So please answer the following question: what is the boiling point of nitrogen? And you answer this question. They even have chain of thought kind of fine-tuning, where you can answer the following question by reasoning step by step, and you have reasoning by step kind of answer. We will talk about more in the next week. They were able to generalize to unseen tasks, right. So this is the question, and you have to answer, but you have to give the rationale before answering. This is the unseen task that was not used in training, and they were able to show that it helps in unseen task, right. That was the prime motivation for using instruction fine-tuning, that you have the instruction. Now you have learned how to use instructions, right, through instruction fine-tuning. Now given a new task instruction, you will be able to perform the task well. So they actually used the data set already used by natural instruction V2, and they had collected some more data set apart from that. So what they created is something called data sets and tasks, right. So from the same data set, you can create multiple tasks, like squared. If you remember, what is the task data set? You have a context, you have a question and an answer, but you can also use it for question generation. Given the context, generate a question for this, right. So you can also use it for question generation kind of task. So from the same data set, you can create multiple kind of tasks, was the idea, and that would hugely boost the data that they would have for instruction fine-tuning. So yeah, I mean, and they use the idea that you can use multiple templates from the same data. Like if you are doing NLI, so you have a premise, a hypothesis, and you have an entailment or no entailment. So you can have multiple kind of templates. Like you put the premise first, based on the paragraph above, can we conclude that, and put the hypothesis, and then you put the options as yes and no. Or I can say read the following and determine if the hypothesis can be inferred from the premise, and then you put the premise and hypothesis. Then you put the premise, can we infer the following, the hypothesis and options, and so on. So you can have multiple templates. So you have data set, from the data set you can create multiple tasks, and then you have even more templates, right. So you've had quite a lot of such data set, task category, etc. templates, and then they would fine-tune on many tasks, right, like common sense reasoning, translation, etc. And they will try to infer on unseen new tasks, right. So this is very similar to supernatural instruction thing, right, but they had more data in task types. And they saw, if you compare with GPT-3, zero shot and few shot, the Flan model, which is slightly less number of parameters than GPT-3, was able to outperform GPT-3, right, in zero shot setting. It was able to outperform even the few shot of GPT-3 through zero shot, right, for unseen tasks. So this was something very, very interesting. So what are the kind of models that they had? So they started with two different architectures: T5 model, that is encoder decoder, and palm model, that is decoder only, right. So they used both the models, and which had their different pre-training objectives, but now you will instruction fine tune them. So only predict, given the instruction and the input, predict the output, like next token prediction. So what they were able to show, that while the pre-training may take a lot of compute, like here 1.8 e to the power 20, the fine tuning, the instruction fine tuning is like just 1.6% of that, right. So very small percentage of the pre-training compute, but that can give you a huge boost in the performance on unseen tasks, right. You can get an instruction fine tune model with like just 1 to 2% of the budget that you used for the pre-training, right. And this gives a huge boost. I mean, this is the T5 model with the corresponding Flan T5, that is the instruction fine tuned model for T5, and they are measuring the few shot prompting accuracy. So once you have instruction fine tuned, you give the instruction, you give few examples, and let it do the task, right. And what they found, this is a huge improvement from T5 to Flan T5, right, across parameters, right, across parameters. And if you go for large high number of parameters, you have even more improvement. So that was something very, very interesting, and that's why this Flan T5 models are one of the most popular models used nowadays whenever you want to do instruction fine tuning for a task. Okay. So now a lot of data sets have been generated by humans, like natural instruction is what we talked about, right, and there are others like P3, Big Bench. They were mainly prompts, okay, and Dolly had a lot of instruction input output examples, and there is multi-instruct, right. So there are a lot of data sets that are human created, like what data set, what Dolly did, they also did instructions. So this was a follow up to the Instruct GPT. So they had 15,000 instruction fine tuned examples. So what they did, so just the employees of Databricks, so they set up a contest that the 20 labelers would get a big award, and they have 7 different tasks, and you can see they were like interesting tasks that typically people will use in assistants, right. And now you can see when you use GPT-4 and all, you ask them like creative writing a poem or a love letter, right, doing summarizing information is again very, very crucial task that people do. So you have a document, you summarize it, like extract information, open question answering, you can give any question and let it answer that question, right, doing classification. So you get 15,000 examples just by, I mean, by the same company, people labeling that. It's like this creative writing category, this was the instruction, what should I do on a free afternoon in San Francisco? And somebody actually wrote this response, and this data set can be further used for now training models. Okay. Now the limitation though for these kind of data sets is that of course you can create, but they require human effort, right. Somebody has to manually annotate this and create this data set, and you may even use it whatever are the annotation instructions available on the web, but they will be limited, right. So how do you increase beyond that the task diversity and complexity? So it's very difficult on that. Now, but what if we can have the models themselves, like the language models themselves, generate these instructions for training, right? So that is where this idea came, the self-instruct, that can I align the models with the self-generated instructions? So rather than humans creating those, can we not create them automatically through machines? Right? So what they did, this was a self-instruct paper. So they started with 175 C tasks, right? So 175 tasks for which they already knew one instruction and one instance, right? So this is what is given to them, task pool. Now we will use that to train a language model in how to generate instructions, right, for fine tuning the model. So they had 3 steps. One is instruction generation. So remember, we will have 3 things: instruction, input, output, right? So first thing is generate the instruction that will define what is the task that you want to do, right? It's like give me a quote from a famous person on this topic. So that's the instruction that you are generating. It can be one of the pool, from the pool, or what language model has generated, right? So you can train the model to generate instructions, different kind of instruction, but that is not sufficient for fine tuning, right? You need instruction plus input and output. Now how do you do that? So they say, okay, so this was something very subtle. They said, okay, so you cannot just directly use that to generate input output. You should see whether what kind of task is it. So they define, is it a classification task or not a classification task? So they say, okay, so that is also not so difficult, that once I have instruction, I can again use a language model to identify if it is a classification task or not a classification task. Like this is not a classification task, right? You are generating something. So if it is not a classification task, like here, so then you say, okay, then what I will do, I'll put the input first. That famous person on the topic, I'll put the topic first. That's the input. The importance of being honest, and you generate a label or a quote on this topic. Honesty is the first chapter in the book of wisdom, right? So this is what you do. But if it's a classification task, like find out if the given text is in favor of or against abortion. So you first generate the class label like pro-abortion, and then generate the input. So that would match that class label, right? I mean, and the rationale that they give is that if we ask them, okay, given this instruction, you generate the input and they define the class, what would happen? There may be some bias of generating about a particular class only. Like you may only generate about pro-abortion or against abortion, right? You may have a certain bias. But if you generate the class level first, you can control it. So you can say, okay, I'll generate class level pro-abortion 50% of the time and against it 50% of the time, and then I'll have to stick to the input, right, accordingly. So that was the reason. Whenever it's a classification task, they will first generate the class label that they can control and generate the input corresponding to that. And if it is not a classification task, then they will generate the input and the corresponding output, right? And once you do all that, you have a lot of instances with this whole thing. You can filter them, like the things that are repeated, you don't want to use them again, and so on. And you can put them back into your task pool so that you train your model to how to generate new instructions, what are good instructions, right? Okay. So like so what they did, they initiate the task pool with 175 tasks, one instruction, one instance for each task, and for every step you will sample 8 task instruction from the pool as in context examples, right? So these are your in context examples, that okay, come up with a series of tasks, and these are the 8 examples, right? And out of it, 6 were from the human written task and 2 were from the model generated one that the model continuously is generating. That they thought would help promote diversity. They will end here and let the model generate. This is what model will generate, a new instruction. Like now once the model is generated instruction, next thing was identify it's a classification task or not, right? So like, can the following task be regarded as classification task with finite output labels? This is the prompt that they gave to the LM, and they define the task. Give me, given my personality and the job, tell me if I would be suitable classification task or not. They say yes. Give me an example of a time when you had to use your sense of humor. It's not a classification time, right? So it's no. Replace the placeholders in the given text with the appropriate name entities, not a classification. So here's some task examples and whether it's classification or not. So these are the templates, and now given this template, now you have to generate some. Now given a new task, you have to say it's classification or not. That's the second step. Now once they do it, I mean, this we discussed why 2 different models, because the input based approach for classification can generate input biased towards one particular class label only, right? Like they give example for grammar error correction. If your task is grammar error detection task, right? It's a classification task, it's a grammatical error or not. But if you want to generate input, it typically always generates a grammatically correct sentence. But if you first generate a label, generate a grammatically incorrect sentence, then it will generate something incorrect, right? So yeah, I mean, then they define, say, classification or not. If classification, then they will do output first, the label first, then the input. Not a classification, the input first, then the output, right? And then you have the instruction input and output pairs. So here's an example of input first. So not a classification. They come up with examples for the following tasks. Try to generate multiple examples when possible. If the task doesn't require additional input, you can generate the output directly. And tasks which exercises are the best for reducing belly fat at home, and you have the output. Like turn down the job offer by sending an email to the recruiter, explain the reason, you have the output. So these are the 2 in the prompt, 2 examples, and then you say instruction for the target task. Okay. For output first, on the other hand, they will first have the class label and then the sentence. Right. So which of the following is not an input type? and class label is E. So, we will generate E task instruction accordingly. So, finally, once you have generated the instructions, so they will filter them. So, they say okay, I will add a new instruction only if the usual similarity with any of the existing instruction is less than 0.7. Right. So, it should be diverse to the existing instructions already. Now, you exclude instruction that contains some specific keywords like image, picture, graph that cannot be processed by language models. You filter out instances that are exactly the same, that are the same input but different outputs, that also they removed, because instruction is same, input is same but output is different, so they removed that. And they also removed the invalid generations and filtered them, like if the instruction is too long or too short, they removed it. It's a repetition of the input, they removed it. So, they had certain filtering criteria, and that's how they came up with this final set. And here's some example that the model generated. Like this is the instruction, given an address in city, come up with the zip code. This is the input, and the output is the zip code, right? Write a letter from perspective of a cat, and there is no input, just have the output. Dear owner, I am writing to you today because I have a problem. Right, you are not as affectionate towards me. I mean, it's a letter from perspective of a cat that the model is writing. And how to write a code for converting degrees Fahrenheit to Celsius. You have the corresponding code here. So, the model has generated all three: instruction, input and output, through which you can train instruction fine tune the model, right. So, they were able to generate like 52,000 instructions, 11,000 classification, 40,000 non-classification. And what they found, I mean, they had used GPT-3. They further instruction fine tune GPT-3 with this data set that they generated, right, with supernatural instruction, and they found that this was able to give them a boost compared to the previous GPT-3 model, right. So, the self-generated instruction actually helped them achieve better performance, right. That was a nice result, that you can actually generate instruction through models, and you can increase diversity by controlling this process, and that can help the model even gain performance on tasks. Okay. So, I mean, in terms of benefits, the main benefit is that whatever you want to describe the task, you can describe it in language, right, in instruction, rather than giving input output examples for the model to learn, or what is the task you wanted to do, right. So, you want to describe in the task semantics itself in language. It's cheap to collect, of course, at a certain level. You can collect it from the web, annotation instructions, data set you can generate, but difficult to scale further, right. It has been shown to do very good in cross-task generation. Also, it's a quick learner, right, and user friendly, because now once you have instruction fine tune model, I mean, what you have to do is to describe your task using natural language, and give the input, and it will perform the task, right. So, it becomes very user friendly, the interface becomes very nice, right. So, okay, so this was our discussion. Chapter 12 of the book describes this in some details, and we will continue from here and go towards the next part, that once we have instruction fine tuned our models, now how do you take them forward, right, as making them as assistants. Okay.